How does railway track turn from this into this? These are wet beds, an issue that occurs with the track ballast that turns it from a nice collection of stones into either slurry in the wet weather or a hard concrete-like mass in the hot. It occurs due to issues within the track bed and leads to a number of issues for the maintenance teams. Wet beds reduce the vertical support to the track, lead to track geometry faults such as dips, twists or cyclic top. They reduce the lateral support of the track, reducing its resistance to lateral forces such as thermal forces. This in turn increases the likelihood of buckles. It can lead to reports of bangs or rough rides from train drivers travelling over that section of track. It further reduces the ability of the water to drain through the ballast, therefore increasing the issue. This means wet beds grow over time, both in their number and their severity. This in turn leads to an increase in the level of intervention that is needed. Early intervention is key, as acting when the problem is small means the least amount of work. So now you can see that wet beds are an issue that reduce the performance of the track bed, lead to maintenance problems, and also are a significant piece of work to remove. Before we get into the causes of wet beds, I have said they cause issues with track geometry. Do you know the meaning of can? Do you know how to calculate it? Know the difference between cant and cant deficiency? No? You can with my free guide to cant ebook. Simply sign up at the link in the top right hand corner or in the description below. If you want to dive even further into the world of track geometry, check out my track geometry bundle. All you need on horizontal and vertical alignment. So, what causes wet beds to form in the track? There are four main underlying causes that lead to wet beds, or wet spots as they're sometimes called, forming. They all centre around the track bed and below. Let's take this cross-section of a railway and label up some key parts of the area below the sleepers before we start looking at the causes. Firstly, we have the ballast itself. It supports the track both vertically and laterally, while also allowing water to drain through it. In the top right-hand corner now is a link to my video that covers the full functions of ballast on the railway. Check it out. Under the ballast, there is a layer known as the formation treatment. This may be a sand layer, known as the sand blanket. There will likely be a membrane or geosynthetic laid out below the sand. In fact, the sand can also be completely substituted for a geosynthetic blanket. Other treatments include capping layers of hard material to give additional support. The exact formation treatment varies due to local conditions. It is there to provide separation between the ballast and the ground below. The ground below may be natural ground or could be made ground if the track is on an embankment, say. The makeup of the ground below is dependent on the local conditions. It can be sandy and free draining, or it could be clay that prevents water running off easily. It is the limitations in the local conditions that the formation treatment will be designed to address. Lastly, there is the crossfall. This sloping of the track bed helps direct the water towards the edge, or cess, of the railway to drain it away. It provides a low resistance path for the water, or that's the theory. It's worth noting that it can also fall the other way at times, such as in platforms or if there is a drain running down the centre of the track. Right then, on to our four failure modes that lead to wet beds. First up, and I hate to disappoint you, is that it happens naturally. Ballast contains a certain amount of dust, even brand new ballast. It's why dust masks are mandatory in a number of countries when ballast is being dropped. The dust is created from the movement of the ballast stones against each other. If this dust is mixed with water, it forms blockages between the individual stones, which then reduces the drainage of the water through the ballast. The dust can be reduced by ensuring the ballast is properly handled up to the point it is dropped, but also screened at source to remove as much of the dust as possible. This type of failure takes a long time, unless the new ballast supplied contains very high levels of dust initially, of course. Second is attrition. This type of failure occurs when dust and other small particles are created by the grinding of the individual stones against one another or against the bottom of the sleepers. The grinding is caused by the movement of sleepers, due to instability or movement within the track bed, such as voiding. Voiding is where the sleeper is not fully supported and dips down when subjected to the load of a passing train. The use of tampers or tamping equipment which vibrate the ballast also have the same effect of grinding ballast stones against each other. The area this failure mode occurs is, you guessed it, directly below the sleeper. The contamination or degradation of the ballast then progresses downwards further into the track bed. This then becomes a cycle, unfortunately, with the instability or voiding of the track getting worse, which causes more movement, which increases the rate at which the ballast degrades and produces dust, which then prevents more water leaving the track bed. The track bed then becomes more clogged, further reducing its support for the track itself. Throw in some tamping or maintenance works to try and address the track movement, which in turn creates more dust, and you're on a hiding to nothing. Our third failure type is surface contamination. It isn't only dust from the ballast itself that can clog it up. A common issue is contaminants getting onto the track from an external source. So what do I mean by contaminants? This is a wide-ranging term for basically anything that shouldn't be there. Diesel and oil from trains, coal, sand or other materials that might have been dropped from wagons or freight trains. In cuttings, soil could be washed down during heavy weather onto the track, not enough to be classed as a landslip, but enough to get into the ballast and start clogging it up. Degrading vegetation or leaves that fall onto the track can also be an issue. This type of failure, as you can imagine, also progresses downwards into the ballast and track bed. Again, it only gets worse as water retention increases, creating and worsening track instability. So lastly, formation failure. And this one is a buy one get one free. Formation failure is actually two failure modes, as it can occur in two main ways. The first way is the formation can fail from dynamic load. Typically, this is seen where the depth of the ballast between the sleepers and the underlying formation or ground is not deep enough. Usually the failure occurs in the track support zone, where the force of passing trains is transmitted down through the rails, sleepers and ballast into the ground. With the reduced depth of ballast, the force is more concentrated when it gets to the formation and ground underneath than otherwise it would be. This leads to it starting to deform the formation itself. This deformation then creates pockets in which water gathers. The water in turn starts to erode the area around the interface between the ballast and the formation, allowing the pocket to grow. This failure type progresses upwards, aided by the pumping action created by passing trains. As a train passes over a section of track, the load pushes the track down, increasing the pressure in the pocket areas, pushing out the water. Once the train has passed, the load and pressure is decreased, and the water rushes back in, similar to how a pump works. This movement of water spreads the contamination through the track bed, again increasing the issue in the track along the cycle we've already seen in the other failure modes. This second type of formation failure that we're going to look at might seem like a repeat of what I've just said, but it is different, I promise. It is also a very specific failure type, known as water-affected interface. It occurs when water is retained at the ballast formation interface. I can hear you saying this is exactly the same as the last failure mode, but in this type of failure, the main reason for the water being retained is due to well-meaning works to remove the issue not being carried out properly. The cleaning of the ballast, or full replacement, is the way to remove wet beds. But if the renewal or cleaning isn't undertaken wide enough across the track to allow the water to drain out of the track bed, the new ballast creates a nice area for the water to sit in. With the pumping action we've already covered, as well as the water acting as a nice lubricant for those ballast stones to grind up against each other, the clogging of this nice new ballast is inevitable. So, to summarise, wet beds can be caused by the contamination and clogging of the ballast, either from above or below. This then causes retention of water and track instability, which then increases contamination further. All the failure modes we have covered become a worsening cycle that leads to ever-increasing issues. So, what can be done? Removal. It is as simple as that. Complete removal of the clogged ballast and replacement with new ballast, along with any works to repair the formation that may be required. Then, ensuring that the track is correctly packed to remove any dynamic movement that would cause the creation of dust and fines. As we saw from the last failure mode, the renewal of the ballast needs to be to the full width of the track bed to ensure that the water can naturally drain away and isn't retained in that nice new ballast. Thank you for watching. Now you know all about how wet beds are formed, the issues they cause and how to remove them. Please do give this video a like, hit that subscribe button, and if you have any questions, drop them in the comment section below.